Our next lesson in Chapter 7 is 7.4, Evaluate Logarithms and Graphing Logarithmic Functions. We're going to start with a little review from 7.1/2. Graph y equals 3 to the x, and then we're going to include some content from Chapter 6 and its inverse. Anytime we see inverse, remember that's the definition over the line of the reflection over the line y equals x. Let's go ahead and draw that in on our graph on the right. And our goal is going to be to create the inverse for this exponential function. If we sketch this graph first, I'm just going to make a table of some values. Now a technically equals 1, so this is like saying y equals 1 times 3 to the x. So when I pick values for x, we're just going to pick our basics, -2, -1, 0, 1, and 2. If we plug in -2, 3 to the -2 power would be the same as 1 over 3 to the +2 power, which is 1/9. If we pick -1, 3 to the -1 power would be 1/3. If we pick 0, 3 to the 0 power is 1. 3 to the first power is 3, and 3 squared is 9. Go ahead and plot those 5 ordered pairs on your graph and sketch the curve for that exponential function. For this graph, we do not have to draw in the asymptote. Hopefully your graph looks something like this when you're done. Remember, your function should not cross over the x-axis. Now, by definition, when we sketch the graph for the inverse, we just take those original values and we reflect them over the line y equals x by switching them around. -2, 1/9 would be 1/9, -2. Should be a 9 right there. There we go. And then 1/3, -1, 1, 0, 3, 1, and 9, 2. Go ahead and plot these 5 points and we'll see if we get that true reflection over the line y equals x. And if you look at those points that are plotted in red, it looks like they're the reflection of the points on the equation y equals 3 to the x. To determine the equation for that line in red, we're going to follow the 4 steps that we did back in Chapter 6. Step 1, you always want y equals. Well, we already have that. Step 2, you want to switch x and y around, just like we did in our ordered pairs. Now, step 3, we're supposed to solve for y. If y is an exponent, we could take the index with a radical, but then that would just put it on the other side with x. So actually, what happens in step 3 is we get stuck. We really can't get y by itself in this equation. So we've come up with a way to write the equation without having to get that y variable out of that exponent position. Mathematicians actually created a term to do this. The inverse of an exponential function is called a logarithmic function. And we call it, or we just use the first 3 letters usually as a prefix for that term, so that we don't have to write out logarithmic or logarithm every time. So here's how we can make it work. If you have an exponential function, the first thing we do is we just kind of rewrite the left side and the right side, but we don't switch anything yet. So notice I just put the bx on the left and the y on the right. Then if you switch x and y, you would have b to the y equals x. And then we do something that I like to call loop it. We're going to use that prefix log, and we're going to use all the parts in the original equation for our new equation. Therefore, step 1 would look like this. If y is on the left and 3 to the x is on the right, we're just going to reverse that completely. 3 to the x equals y. When we switch x and y for this is kind of where we got stuck up above, that would be 3 to the y equals x. So notice 3 is the base for that exponential statement. To loop it, we start with the prefix log. So I'm just going to write log. The base of the exponential function becomes the subset base of the logarithm. So that's where that 3 goes. So there's your base. like so. And then the looping comes from this. From the base, we always take the logarithm of what's on that left-hand side, or excuse me, the right-hand side, which is x. And then it always will equal the exponent. And that's how you get y by itself. But then if we want to write y first, we would just write y equals, we write that log prefix, base 3 of x. This is the equation for the inverse of that exponential function. Notice we don't have to write y negative 1 because the log is what's doing that inverse for us. So this is the equation for the inverse. So there are lots of things we can do with this logarithmic kind of term. When asked to simply convert forms, you're not going to do the whole inverse rule. You're just going to do the looping part. Here's what I mean. Rewrite the equation in logarithmic form. So that means you have to use that log in your answer. 2 to the third power equals 8. That's a true exponential statement. But to simply rewrite that in logarithmic form, notice the base is 2, so when I write my log prefix, I keep the same subset base. And then the looping comes from here. The logarithm base 2 of 8 equals, you guessed it, the exponent. It always equals the exponent on the right-hand side. And that's how you rewrite the form. We don't do anything else with it. Try the next one. 4 to the 0 power equals 1. Another true exponential statement. If the base is 4 and we start with that prefix log, it's just log base 4 of 1 equals 0. You're just literally following that looping method and rewriting from an exponential statement to its logarithmic kind of counterpart. Try the last one. 7 to the first power equals 7. Notice the base is 7, therefore log base 7, now this looks kind of weird, of 7, so there's kind of 2 7s in a row. Please make sure to differentiate the little sub base 7 to the 7 that's written afterwards. And what should it equal? Always equals the exponent of 1. And that's just converting from exponential to logarithmic form. Now when we flip-flop that, to rewrite in exponential form, you should have no log when you're done. We want to get rid of that. That means we're going to take that subset base and make it the base for the exponential. And we still do the looping. So it says log base 3 of 81 equals 4. If the base is 3, that's going to be the base for our exponential function. So remember up above when we did the looping, our answer on the right-hand side was always the exponent. Therefore, when we loop it now, it's going to be the exponent again. But it's not going to be 3, it's going to be 4. Whoops, there we go. And that will equal whatever we were taking the logarithm of at the time, which is 81. 3 to the 4th power equals 81 is just that logarithmic statement rewritten in exponential form. Now here's something that's unique in the next one. It says log of 1,000 equals 3. So if no base is written, then it's automatically, that's a question mark right there. If no base is written, then this is going to be called a base 10 logarithm. And that's called a common logarithm when the base just defaults to 10. Kind of like when we did radicals, and if we didn't write a number as the index, it was the square root. It just kind of defaults to that value. So because of this, we're going to start with the number 10. We'll raise it to the 3rd power, and you guessed it, it equals 1,000. When we're asked to rewrite forms, we're not doing any evaluating or simplifying. We're truly just rewriting. Last but not least, log base 1/2 of 32 is equal to -5. Again, that little sub number right there is our base. 1/2, so since it's a fraction, I'm going to put it in parentheses, kind of like how it's written with the logarithm. Raise it to the -5 power, and that would actually equal 32. And that's just how you work with rewriting forms. You may have noticed the log and the ln buttons on your calculator. It's possible on occasion to use your calculator to evaluate, but it doesn't work for everything. Here's why. Like I said up above, when you don't have that logarithm base already written, it defaults to base 10. So anything that's base 10 is calculator friendly. But if it's not base 10, it isn't calculator friendly. And we have to use probably our power chart. Oh boy, there that is again. We'll probably have to use that to help us. So again, if it's log and there's no base and it defaults to base 10, that's called a common logarithm. And if you have ln, a natural logarithm, which is kind of weird because it's natural logarithm, but this is ln. So it's not an in, it's ln. Natural logarithm is the inverse and anytime you use e as your base. So it says, what is the base of each logarithmic expression, whether it's a common logarithm or a natural logarithm? For log of 100, the base is 10. But for log base 2 of 32, the base is 2. For ln, the unique thing about ln is that it'll never have anything written because it's always base e. And that's what it says up above, only in all caps. That's because it's always base e. So if I'm ever trying to trick you, like the next one, ln 3 of 5, you can't have 3 with ln, so this one's not possible. The base doesn't work. It's not base 3, it can only be base e when you're using ln. Let's finish up the lesson by doing a little work with evaluating. If you're asked to evaluate without a calculator, it's because you can't use your calculator to solve. So we're going to have to rely on a power chart more than likely, or maybe some guess and check, but without a calculator. So this would be a great time to grab a power chart from either chapters 5 or 6 as a resource if you need it. Evaluating means you want to figure out what this equals. We're not just rewriting forms, but rewriting forms would be a way to help us. For example, log base 7 of 49. If you're asked to evaluate it, a great way to attempt that would be to try to loop it. But notice it's not an equation. So we have to set it equal to a variable. So I'm just going to pick n as my variable for these. If I loop it then from logarithmic back to exponential, my base is 7. That would mean 7 to some power has to equal 49. So you either maybe know this answer already because you know the connection between 7 and 49, or you could use the power chart and find where row 7 is to see what column you need to get to 49. And this just means n would equal 2, since 7 squared is 49. So log base 7 of 49 equals 2. Let's try the next one. Log base 9 of 1. Again, if we're trying to figure out what this is, let's try that looping method. We'll set it equal to n. So we would have base 9 to what power? Equals 1. And hopefully we know this answer already because this actually isn't on the power chart. No, it might be. No, I don't think it is. What power gives you an answer of 1 every time? That would be 0. Or 9 to the 0 power equals 1. The next one, log of 1,000. So technically, this one's calculator friendly, but let's see if we can navigate it without a calculator first, and then we'll go from there. Since the base isn't written, we know that it's going to be base 10, and we don't have an equation, so we know we're going to set it equal to n, and then we'll do our looping. Log of 1,000 means, in exponential form, 10 to the what power equals 1,000. And if you use your power chart, or if you know this answer, that'd be great, you would get n equals 3. They're not always super easy answers. Let's try the next one. Log base 16 of 4. So now notice our number that we're taking the log of is smaller than our base. If we set it equal to n, and we do that looping method, our base is 16. 16 to the n power equals 4. So how do we make a base smaller? Well, something we could do is find a connection between 16 and 4. 16 is the same thing as 4 squared. And you get that from the power chart. And then we have that n on the outside. 4 is the same as 4 to the first power. So on the left-hand side, we have 4 to the 2n, and on the right-hand side, we have 4 to the first. So if the bases are the same on each side, then the exponents also have to be the same. 2n would have to equal 1. So what could we do to get n by itself? We could divide both sides by 2. So this all of a sudden became something to solve. N equals 1/2. 16 to the 1/2 power, which if you recall is the same as the square root of 16, equals 4. And that's a true statement. Try the next one. Log base 81 of 27. Oh goodness. All right, let's try this. Again, set it equal to n, but our base is a whopping 81. And if we raise that to the n power, how on earth are we going to get 27? Yikes. Well, using the power chart, there's a base that we could use that works with both 81 and 27, and that's base 3. So we could think of 81 as 3 to the 4th power. That's a 4. There we go. To the nth power. And 27 is the same as 3 to the 3rd power. So power to a power, we multiply. 3 to the 4n equals 3 to the 3rd. And again, if the bases are the same on each side, then the exponents would have to be the same as well if it's an equation. And now this should be pretty easy to get n by itself. We're just going to divide by 4. Therefore, n equals 3/4. 81 to the 3/4 power would equal 27. And the last thing that we're going to do, please grab your calculator. We're going to round to the nearest thousandth or 3 decimal places. Now you need to be able to find the LOG button and the LN button on your calculator. We can only use a calculator if the base for the LOG is 10, and then anytime we have LN, we can always use our calculator because that's only for base E. Log 5, you're literally going to type that log button on your calculator and then 5 and press enter. And you're going to get approximately 0.699. So here's what that means. If you type in, so this is kind of like a check. Let's go ahead and write that in. I'm going to check. If we take the base of 10 to the 0.699 power and press enter, guess what? You get approximately 5. So we're just kind of doing the reverse of that exponential function. But it only works if the LOG is base 10. So you try the next one. LOG of 0.234 and see what you get. Hopefully you get negative 0.631. And that would mean 10 to the negative 0.631 power is approximately 0.234. Now if it's ln, you do the same thing. You just get that ln button to go first and then press what you're trying to take the ln of. Now I'm kind of throwing a curveball at you at this one. This is a trick question. Anytime you're taking the LOG or ln of 1, that's going to automatically equal 0. There's no rounding there. Because e to the 0 power would be the same as like 10 to the 0 power. It just equals 1. All right, try ln 30. This one will get a bigger answer for. If you type ln and then 230 and press enter, we get approximately 5.438. Rounded to the nearest thousandth. Try the last one, ln of negative 0.67. Something's going to happen here. We're actually going to get stuck. We cannot take the ln of a negative number, so this one's not possible. Unfortunately, we can't take base e or any number base and raise it to an exponent and get a negative answer. A negative answer comes if there's an a value out in front that's negative. So not valid or not possible if the number is negative. We can get a negative answer, we just unfortunately can't take the LOG or ln of a negative number. Whew, and that's it. That's 7.4. Working with logarithms, evaluating, and graphing.